All right, today we're going to be reviewing circuits in a single take, so this will be kind of fun. All right, here we go. All right, so resistor circuits are based on these things called resistors. Resistors are usually made out of some kind of material that allows current to flow through, but not quite all of it. Current, we'll talk about in a moment, but basically it will just let some charges through on a kind of not perfect basis. So if we have a wire, which is a perfect conductor, leading into this material, this would be our resistor, then we can categorize some property of it called the resistance, which is variable R, as basically how difficult it is for stuff to move through it. So we're going to have some property of the material, rho. This is the resistivity of the material that you're using. So the resistivity of the material is basically just how easily does it let charge through, or how difficult is it for charges to pass through. And that will be times the length of the resistor, where L actually goes all the way to the end. There we go. And then divided by the cross-sectional area, which would be the area of this face here. Right, so this would be the length and the cross-sectional area. So if you think about it, you can see that if you have to move through the material a distance L, then the amount that you would have to move through based on, if your resistivity is how difficult it is for stuff to move through, and you have to move through distance L, you can multiply the resistivity by the length L to get kind of a measure of how difficult it is to move through that length. Then we divide by the cross-sectional area because think about it like a large group of people trying to move through a small area, or like a road where you have multiple lanes. The more lanes that you have, the easier it is for cars to move through, because if one car is moving slow, you can just pass them, or you can have 3 cars taking up the same amount of length that only one car would take up. So that makes it easier for things to move through. So the resistance goes down if the cross-sectional area goes up. So this makes sense. Now, we talked about the resistance being also a measure of how hard it is for stuff to flow through the circuit. So we also get that the resistance is equal to the voltage change and by voltage change, I mean if I have a resistor here, it would be, V initial and V final. And technically this would be the voltage drop, or the magnitude of the change in voltage. So the magnitude of the change in voltage. Since we expect V final to be lower than V initial, we would get a negative number here. But if we just want the magnitude, then we just get rid of the negative sign. And I here is the current. Now, current is the change in charge over the change in time, so dq dt. All right, and dq dt gives us a measure of the flow of positive charge. So really this is like the negative flow of electrons, which does get annoying later on down the road, but for right now, just think of it as the flow of positive charge and you'll be fine. So this actually lets us know that the voltage drop across the resistor is equal to the current through that resistor times the resistance of that resistor. So this is the voltage drop. And this is the current. And this is the resistance. Okay. So what I can figure out is if I have some circuit, this is a battery, or this is actually a cell. Why don't we go over the symbols first. So a cell is something that supplies some voltage. A wire is just a straight line. And this we will assume is a perfect conductor. We'll get some resistance, so we'll call a resistor. This symbol, which is kind of a cool one, this will drop some voltage. And so that's pretty much all the things we need. You can also get a collection of cells, which is called a battery. And you just denote that by having multiple cells in line. Okay. So if I want to draw a circuit, I can start with some cell and put some resistor in that circuit. There we go. So I have some cell that's going to give me some voltage across the cell. It gives the voltage from the small end to the big end. So the voltage will go up from this point to this point. So here we'll put 0, and here we'll put plus B. Right? So it will add some voltage. Now the reason I put 0 here is because if you don't have a 0 there, or at least some stable number that this then voltage goes up by, then you'll get an ever-increasing voltage based on it just constantly adding to itself. So if you don't lose all of that voltage here, then you will constantly increase your voltage, and then your circuit will break. This positive voltage here is also sometimes used with this symbol. This is EMF, or electromotive force, which is funny because it isn't a force. It is just voltage. So that's a common thing for it. So we know that the voltage drop across the resistor has to be equal to the voltage supplied by the cell. Because if it isn't, then the circuit will continuously increase in voltage, and that's not good. So basically what will happen is the current will adjust itself to match whatever it needs to be in order to make this a reality, this VR equal V cell thing. So in that case, right, we get that the voltage of the resistor, which is equal to the voltage of the cell, would be equal to IR. Right, so you can find the current if the voltage and the resistance are given. You can find the current for a circuit with I equals V cell over R for this particular setup. But what if we have a slightly different setup? So now we're going to look at things called series. So a series circuit is when you have multiple resistors in a row. So think about Christmas lights. They don't really make them this way anymore because it's incredibly inconvenient. Because this is why, you know, if one goes out, they all go out. Because if this one breaks, well, then you don't have a conductor leading around, and then the current stops flowing. So that's kind of a problem there. So we'll call this R1 and this R2. And again, this will be V cell, just because I want to keep my nomenclature pretty consistent. So we know that the voltage drop across the cell would have to equal the voltage drop across resistor 1 plus the voltage drop across resistor 2. The reason's because that voltage will have to first go through resistor 1, like the charge and current will have to go through resistor 1, then resistor 2, and it will lose some voltage across resistor 1, but then if it loses all of its voltage, it won't be able to go across resistor 2, and then the current will stop flowing and you have problems. So it will set itself up such that the current will allow the two voltages of R1 and R2 to equal the voltage of the cell total. So now we get V cell is equal to I R1 plus I R2. Now notice that I just wrote I didn't write I1 and I2. That's because since these things are on the same wire path, they have the same current. current works such that it is constant along each path. So current current is the same then along the path. So if our path splits, then the current can change, and if the path stays the same, aka you are on one road, then the current has to stay the same. So think about it like a road still, right? You have the same number of cars driving down a road. Even if they come to a stop sign and then they move on, the same number of cars will still be going down that road if the stop sign is just in the middle of nowhere and there's no turn going. But if there's a turn there, then some of the cars might veer off to, let's say, the right or left, and then the number of cars you have going straight will not be the same as the number of cars that arrived at the stop sign, right? So it's kind of like that. So in this case, they're all stuck on one track. So let's think about this more like, a speedway where you have the two resistors might be a mandatory pit stop or something like that, right? They have to stop at R1, they have to stop at R2, and then they can keep going around. But they have to go through both of them. They're forced to. But you still have the same number of cars on the track at all times if these are all mandatory, right? Which they would be in this case, for an example. So that means that we can factor out that I R1 plus R2. And then this here, this is what we're going to call our equivalent resistance for this circuit. So the equivalent resistance is if we redrew this circuit, but instead of our series, we just put a single resistor. Of equivalent resistance. So this is a nice way if you need like a really big resistance, but don't have a bunch of really big resistors, you can actually kind of daisy chain a whole bunch of resistors, and then you will get a big resistance based on that. So REQ in this case then, for series circuits, REQ series, REQ is equal to the sum of the R's in that series. Right. So as long as they are in series with each other, you could have 50 of them in series, and it would just be the sum of all 50 resistances, which is pretty handy. So now let's talk about the other type of circuit you can have, which is called parallel. So a parallel circuit doesn't have them in a line. It instead has them as two separate kind of circuits that are connected to each other, like this. And you can see that these two lines are in fact parallel. That's why it's called parallel. Although they don't have to be drawn this way. They can be drawn however, such that there is some kind of split. Right, so here we have some split. Right, so some current, I'm going to draw out the current now so you can see kind of where it goes. Some current will come out this way and reach this split. Then some of that current will go down, and some other current will go this way. And then when they join back together, they go back to that original value for the current that they were. All right. So in this case, we can see that I total is equal to the sum of the currents. Right? I could have 10 wires disconnect, at this one junction or whatever, and the current would split into 10 different values. And the total current would still be equal to all 10 of them added together. So this is very similar to the equivalent resistance, but in this case, it's more like a total equivalent current, right? So we're going to use this, though, in order to figure some stuff out. That, and combine with the fact that if this is the voltage of the cell, right, the voltage drop across each of these resistors R1 and R2 has to be the voltage of the cell. So V cell equals V1, and that equals V2. This is because if you don't get that amount of voltage being dropped over each of those resistors, then their current will increase such that it will, but also you would get some kind of either your circuit would dissipate or it would overcharge itself, right? So we don't want that. So I like to think of these as sort of like checkout lines at a store. So let's say you pull up to a store you want to check out. You might look at self-checkout and go, oh man, self-checkout is so much faster. It has such a lower resistance, right? Things can flow through there much faster. It has a higher current because it has a lower resistance. And there's a checkout line that has a person checking out items, right? But let's say everyone wants to go through self-checkout because it's so much faster, it's so much more efficient, all of that stuff. So you might think, why would anyone go down the green path when they could go through self-checkout and go down the blue path, which is better? Well, what happens when the line for self-checkout gets really, really long? If the person who's doing, you know, the full-blown checkout where they scan your items and stuff has no one in line, you might be able to go through that line faster than it would take you to go through self-checkout, even though self-checkout is more efficient, even though self-checkout is, you know, better in a lot of different ways. It might be beneficial for you to not take that path because there's too many others trying to go down that path, right? So it's sort of like that whole thing where if Bill builds a building in 6 hours and Terry builds a building in 7 hours, how long does it take them to build a building together? And the answer is something less than 6 hours, right? Because they're working together. So here we know that the equivalent resistance needs to be less than R1 and less than R2. Right? It doesn't matter if R1 is less than R2, but R equivalent needs to be less than either of them. It needs to be less than the minimum between them. So let's figure out what that is. I know that I is equal to V over R. And I know that they all have the same voltage, which is good. So I'm going to do this I total to get V total, which is just the same as all the other V's, over R equivalent is equal to, well, V1 over R1 plus V2 over R2. And now I've already said that all the voltages are the same, so I can actually cancel all of these and just end up with 1 over R equivalent is equal to 1 over R1 plus 1 over R2. So for a second, let's add some numbers in here. We're going to say that R1 is equal to 4 ohms. Now, ohm is the SI unit for resistance. Okay, so that's the SI unit for resistance. So R2 then we'll say is also 4 ohms. So I know that R equivalent has to be less than 4 ohms. So I get 1 over R equivalent is equal to 1 over 4 plus 1 over 4. So that would equal 2 over 4, or 1/2. And then when I invert that, I get R equivalent is equal to 2 ohms. So that means that R equivalent is less than R1 and R2, which is great, because we would expect half the things to be able to go through R1 and half the things to go through R2. It's like if you have 2 checkout lines and both of them are equally as fast. Half the people are going to go through one line and half the people are going to go through the other line. And then you can find the current through each one by doing the voltage drop is equal to IR, where you know the voltage here would be whatever the voltage is. Your R would be 4 ohms, right? And so on and so forth. And then, you know, if you wanted to find the total current, you would just use the equivalent resistance because we would treat them like one resistor. Okay, so the last thing to look at is power dissipation. All right, so we know that the power is the change in work over the change in time. This is old. This is from APC, mechanics. So this is from mechanics. So we know that. And we know that the work done by the electric force is QV and delta T, right? So delta QV, delta T. So the power dissipated by a resistor is going to be related to the change in charge over the change in time. So if we consider the voltage across the resistor to be some constant value, then we can pull the V out and get delta Q over delta T. We can also rewrite this as dW dt if we want to do calculus. Then we get dQV dt, and then this would give us V dQ dt. And we know that dQ dt is just the current. So power is equal to the voltage times the current, and if we want the voltage drop across a resistor is IR. So the power dissipated across a resistor would be I squared R, which is also equal to IV, which is also equal to V squared over R. Because we know that the current is also, right, V over R. So there we go. So we know that this is true for power. So depending on what they give you, you can find any kind of power dissipation based on for your resistor. Okay, and that's actually pretty much everything for this. So yeah. All right. Oh yeah, we also have one last thing, even though I think I said that was the last thing. Kirchhoff's laws. We kind of already went over them, but not explicitly. So I just want to cover these pretty explicitly. There are two. So the first one is called the junction rule. And this one just states that the current going into a junction is equal to the current coming out of one. Okay. So this is what we saw when we did the whole, like, you know, I going in, and then it splits off into I1 and I2 when it reaches a junction, which is, you know, if we have a wire that goes like this and a wire that goes like this. So we would get some I in, and then some I1 and some I2, right? And this is just saying that I is equal to I1 plus I2. So this was how we logicked our way into parallel circuits, was that the current has to split evenly. And this is one of Kirchhoff's laws. It's the junction rule. But it kind of makes a lot of sense when you think about it. And then it also goes vice versa, right? So if I have, you know, a current coming in this way and this way, so if I have some current here, I1, or we'll call this I3 and I4, and then this would be some I, then I3 plus I4 is equal to I. So all the current going into the junction has to equal all the current going out of the junction being this spot where the wire can go into multiple places. All right, law number 2. I honestly cannot remember the name of this one off the top of my head right now, but it's a path-based one. So I'm just going to call it path law. That's not his name, but whatever. Path rule, something like that. I said I'd do it in one take, so I'm not going to go look it up. Sorry, not sorry. All right, so this one says that the total voltage around any, well, total voltage change around any loop. Oh, that's what's called. Boom. Loop rule. That's what's called. Is 0. So what that means is if I have a cell going this way, and then I have, let's say, some resistor here, and I have another resistor here, and then this is going to come back down and go in here. So I basically have the same parallel circuit that I had before. You know, the voltage on this path, where I go around the outside, the change in voltage, so if I say that the battery is plus V, and this is, we'll say R1, and this is R2, then that means that V has to equal I R1, because that would be the voltage drop across resistor 1. And, or really it would say that VR minus IR1 is equal to 0. Since this would be an increase in voltage, this would be minus IR1 as my change in voltage there. And then I know that the change in voltage around any loop has to be 0. So that means that V minus IR1 is equal to 0. Now we get another path, which would be this one. Boop. So this path, we would get that V minus IR2 is also equal to 0. And that makes sense because we know the voltage drop across R2 has to also be equal to V, as we saw for our parallel circuit. Otherwise we get some kind of a short and it's not very fun. Where this is cool, and where we haven't really talked about it so far, is with inner loops. So like this one right here. So if we go this way, then we go this way, and this way. So let's make this a loop now. Well, this one, when we start, we drop by some IR1. That's our starting thing. We're going to drop voltage by IR1. But then we're going to go backwards across R2. So I'm actually going to add the voltage from R2. Because I'm going, you know, I could think about it this way, which I'm going to drop IR2, but my current in this case would be negative. So actually I'm just going to rewrite it like this. Because I'm going the opposite way of the path is opposite the direction of the current. So I would get IR1 minus IR1 plus IR2 is equal to 0. So I actually get 3 equations here with, you know, however many unknowns you need. But I have 3 equations here. So I've got IR1 plus IR2 equals 0. And I've got V minus IR1 equals 0 and V minus IR2 equals 0. So those are all 3 valid equations that come from the loop rule. And that's actually done.